Hello, everyone, and welcome. So, today we're not going to do some boring math lecture, okay? Instead, we're going to solve a mystery. Did you know that every single square matrix has a secret identity? It's like it's leading a double life. And today, our job is to uncover that secret. So, are you ready? Let's get our detective hats on. This is going to be fun.
Okay, so our investigation starts now. Just look at the screen. What do you see? It looks like a normal, simple square matrix, right? But is it? Could there be something hidden inside? Well, that's the big question, and that's the case we are going to crack today. Let's find out if this matrix has a secret identity.
All right, let's look at our first suspect in this case. Suspect number one, I like to call it the mirror matrix. Now, this is a special kind of identity. The real name, it's a little technical, but if you just remember mirror matrix, I promise you will never forget it. So let's see what this is all about.
Okay, so here's the official name. It's called a symmetric matrix. And you know what? The definition is super simple. A square matrix, let's call it A, is called symmetric if and only if its transpose, that's A prime, is exactly the same as the original matrix. So, simply put, A prime equals A. And just in case you forgot, what's a transpose again? It's easy. You just swap the rows and columns. That's it. Now, how do we remember this? I have a great trick for you, something you'll totally get. Think of a symmetric matrix like it's from mutuals only. You know, on Instagram, if you follow your friend and they follow you back, you're mutuals, right? It's perfectly balanced. It's exactly the same here. The element in the ith row and jth column, aij, is always equal to the element in the jth row and iv column, aji. See? Perfect balance. And look at this. This makes it crystal clear. On the left, here's our matrix A. Now we find its transpose. What do? We take the first row and make it the first column. We take the second row, make it the second column. You get the idea. Now look at the result, A prime, on the right. Just look at it. It's identical. Exactly the same. There's literally no difference. It's like the matrix A is looking in a mirror and seeing itself. And that, my friends, is why we call it a symmetric matrix. Okay, one suspect down. We figured out the mirror matrix. So, time to move on to suspect number 2. And for this one, let's call it the opposite matrix. I think the name gives you a pretty big clue, right? It's basically the total opposite of our mirror matrix. Let's investigate this one. So the official textbook name for this one is a skew symmetric matrix. And the rule is also simple, but you have to be careful. The rule is A prime equals negative A. You see that minus sign? That little guy is everything. It's the most important part. It means when you find the transpose, what you get is the original matrix, but with every element sign flipped. It's the negative version. And to make this stick, let's use another analogy. Think of this as an influencer fan matrix. Imagine an influencer, I, has a positive impact on a fan, J, let's say a value of +5. But then, the fan leaves a mean comment, so the fan has a negative impact on the influencer, -5. See? It's a totally opposite reaction. And that's exactly the rule for skew symmetric matrices. Aij is equal to negative Aji. Okay, now listen closely, because this is the biggest clue of all, the smoking gun, the one thing that helps you spot a skew symmetric matrix from a mile away. Are you ready? The diagonal elements are always 0. I'm not kidding, always. But why? Well, the logic is actually really simple. We know the rule is Aij equals negative Ajj. Now, for the diagonal elements, the row number I is the same as the column number j, right? So the rule becomes Aii equals negative Aii. Now you tell me, what is the only number in the world that is equal to its own negative? 0. That's it. This is a super important trick. Remember it. It'll save you so much time. Let's see this in action. Let's prove it. On the left, we have this matrix B. And what's the first thing you notice? Yep, exactly. All the diagonal elements are 0. Okay, so now let's find its transpose, B prime. And look at what we got. Compare B prime to the original matrix B. Every number is the same, but the sign is flipped. So B prime is just the negative of B. The rule, A prime equals negative A, is proven. It works perfectly. All right, so far, we've investigated our two main suspects, the mirror matrix, which is symmetric, and the opposite matrix, which is skew symmetric. But what do they have to do with the original matrix we started with? What's the connection? Well, it's time for the big reveal, the moment you've been waiting for, the climax of our detective story. And here it is. This is a super important theorem. It says that any square matrix, I mean any single one, it doesn't matter what it looks like, can be written as the sum of its two secret identities. A symmetric part, which we'll call P, and a skew symmetric part, which we'll call Q. So basically every matrix is made up of these two parts added together. It's just A equals P plus Q. Simple. So now the big question is, how do we actually find these two parts P and Q? How do we separate the matrix into its secret identities? Well, it's actually really simple. We have two, let's call them magic formulas. These are your detective tools. To find the symmetric part P, the formula is half of A plus its transpose. And for the skew symmetric part Q, the formula is half of A minus its transpose. You absolutely must write these down. These formulas are the key to everything. Okay, enough theory. Theory is good, but practice is better, right? Let's actually use these formulas now. We're going to take a real example, a live case, and we're going to crack the code. We'll find the hidden symmetric and skew symmetric parts of a matrix. Are you ready for this? So for our case study, we're going to solve an example straight from your NCERT textbook, example 22. Here's the matrix. Let's call it B. Our mission, should we choose to accept it, is to break this matrix B down into its symmetric part P and its skew symmetric part Q. And please pay close attention here, because this exact type of question comes up in exams all the time. And don't worry, the process is really simple. It's just 4 easy steps. Step 1, we find the transpose of B, that's B prime. Step 2, we use our magic formula to calculate the symmetric part, P. Step 3, we use the other formula to calculate the skew symmetric part, Q. And finally, step 4, the final check. We add our P and Q together to make sure we get our original matrix B back. It's a great way to know if you got the right answer. Okay, let's go. Okay, step 1, find the transpose. On the screen, you can see our original matrix B. Now, to get its transpose, B prime, what do? We just swap the rows and columns. The first row becomes the first column. The second row becomes the second column. The third row becomes the third column. That's it. Step 1 is done. See? Super easy. All right, moving on to step 2. Let's calculate P, the symmetric part. Remember the formula? P is half of B plus B prime. So first, we add the two matrices, B and B prime, element by element. Then we take that result and divide every single number inside by 2. And voila! Here is our matrix P. And just to check, look at it. It's perfectly symmetric. See how the elements across the main diagonal are mirror images of each other? Perfect. Great. Now for step 3, finding Q, the skew symmetric part. The formula is almost the same, but with a minus sign. Q is half of B minus B prime. So we follow the same process. We subtract B prime from B, then we take that new matrix and divide every element by 2. And there you have it, our matrix Q. And look, what's our big clue? The diagonal elements are all 0, and the other elements are opposites. It's a perfect skew symmetric matrix. And now the moment of truth, step 4, the final check. This is where we see if our detective work was correct. What happens if we add our P matrix and our Q matrix together? Will we get back our original matrix B? Let's do the addition. And yes, it works! P plus Q gives us back the original matrix B exactly. So, case closed. We've done it. We've successfully found both of the secret identities hidden inside matrix B. So, before we finish, let's quickly recap what we learned in our investigation today. First, a symmetric matrix is our mirror matrix, where its transpose is equal to itself. A prime equals A. Second, a skew symmetric matrix is the opposite matrix, where its transpose is equal to its negative. A prime equals minus A. And what's the biggest clue for a skew symmetric matrix? Yes, the diagonal elements are always 0. And the most important discovery, any square matrix can be written as the sum of a symmetric part and a skew symmetric part. And of course, now you have the two secret formulas to find them. So, the big takeaway here is that you now have the power to find the hidden identity of any square matrix you see. You're officially a matrix detective. And, this is just one example. Math is filled with these beautiful hidden patterns and secrets. So my question to you is, now that you've solved this mystery, what other secrets are you going to discover? Keep asking questions, keep exploring, and keep learning. I'll see you in the next one.